So the idea of this seminar here is just to present some ideas behind category theory, just to 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 do a little invitation, like some kind of introductory exposition to some of the ideas of this theory. And so the inspiration for this seminar here uh, came from another seminar from Emily Riehl, named From Arithmetic to Category Theory. And in this seminar, she presents a really basic identity of arithmetic and use some of the ideas of category theory to prove this identity. And in this seminar, she gave for us a little exercise that is to prove these two identities. So now in this seminar, I will just do this one. So our goal here is to prove the following exponentiation rule as a in the power of b plus c equals a of b, power of b, times a of c. And to do that, we'll go into some of the ideas of category theory. And the first one that we will going to do is the categorization of this equation to transform in some kind of um, an isomorphism between two 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 sets in this case. And with that, we're going to use an universal property that I will explain later to really assure that that isomorphism will be correct. So the next step we will just do is get these things together to become a proof. So the next step is categorification, like I said. And the idea of this process is to transform some set theoretical expressions or results in categorical results. So to do to do that, one could think that what we were going to do is the abstraction of some sense, in some sense, of some kind of result. In this case, this identity. So for this abstraction to make any sense, we need to think first in what is the purpose of these elements in this equation. So for example, we have some operations here, some operations here, and some elements, in this case, the natural numbers. So for doing this categorification, for doing this abstraction, we're going to need to think what are we going to abstract, what we're going to uh, forget in this equation, and what we're going to focus, what is the essence of this equation. And one of the possible answers to think what are the purpose of these natural numbers here is that they represent, they are the cardinality of some finite sets. So and it is the philosophy that we are going to use here. So we're going to for every natural number we will find a set that's not hard to find. It's really a canonical way to find that, such that its cardinality is that natural number. So as we can see in this equation, we just use three natural numbers. So we could choose three sets such that their cardinalities match with these three natural numbers. So an equation like A equals B becomes the cardinality of the set A is equal of cardinality of set B. So in set theory, that result means that we can construct an isomorphism between these two sets, such that two isomorphisms, two bijections, né, between these two sets, such that the composition in any side, like position of G with F and F with G, becomes the identity of these sets. So it's like another way of saying just that these sets are isomorphism, like they're bijective. I don't know, it's the term. So for now, what we done, what is the takeaway from this process is that we can can transform this equation, this this equation in a in a more abstract way through a isomorphism between sets. In this case, the sets are defined by its cardinality. I mean, it's based on this other one equation that we want to prove. So the next step is to think what are the equivalence between the operations in here in the natural numbers, these three operations we have in this identity, to this analogy we're making with the cardinality of sets. So starting with the addition operation, we need to think if I have one set with this cardinality and another with that, what is the set of the cardinality? What is the set that has cardinality a plus b? It's not that hard to see. It's like a simple result from set theory that the disjoint union between the sets A and B has this cardinality. And just from an illustration, if we have a set A with three elements and set B with two elements, the disjoint union we will have no, the disjoint union will have a cardinality 5. It's just a simple example. The next step, the next thing we're going to need to do based on that equation is to think what this multiplication operation has to do with the cardinality of some set with uh, with that with that cardinality. So in another way of saying, if I have a set again A with a cardinality little a and a set B with cardinality little b, lower b, what is the set that has the cardinality a times b? So it's simple again. The set is the Cartesian product of a with b, a times b. So just fun illustration again. Not the purpose was to simplify this. You have to illustrate, but the illustration was not good. But the idea is that for every element, we're going to encapsulate the possible other elements, and making that is gives us a set with cardinality a times b. The next operation is the exponentiation. So again, thinking of a set with that cardinality, what is the set that we can construct with this cardinality over here? I don't know if that is well known or is a little more mysterious, but the set is the set of the functions between b and a. So the idea here is that for for a set to be this cardinality, we just have to pick the possible functions between the set B, 2A, and the cardinality of this set that will denote essentially like this. we will have this cardinality. For illustration here, it became more confusing, I don't know. But here I just illustrate four different functions that we could possibly write, I don't know, uh, from this set to this one, and that is the notation we're going to use. So putting all this together of what we know, of what we construct, we can translate the other identity, that this one that we want to prove, to this isomorphism. This, just remember, this notation means the set of functions from the disjoint union from of B and C to A is isomorphic to the Cartesian product of these sets, and these sets are the set of functions from B to A, and this one is the set of functions between C to from C to A. So the idea of this categorification, actually, a better term would be translation, is that we translate this equation to this one. So we can, instead of thinking about equations, we can think about morphisms that we can go from this set to this one and get back, because they are bijection. I use this term categorification because there, there is um, this process in category theory that we translate terms from category set theoretic uh, properties theorems to categorical theorems that we are going to use later in some point of this presentation. But for now, a better term could be a translation from uh, natural numbers results to set theoretical results. So to assure this isomorphism, we're going to use a universal property that holds for this category of sets. Or saying in another way, is a property that we're going to have in set theory. So think now in universal properties. We can now think of what this set really means. What is the set of the disjoint union of B and C to A has to do in, has to offer for we to make this proof. So thinking a function of this set that goes to the joint union of B and C to A, and uh, we'll notice that for every B or every little b in in this in this union, or particularly in the every little b in the set B that is is contained in this union, we'll have a f of b in A that um, such that we construct like a smaller function from B to A that takes every element B and sends to the f of B, this f in the case. And analogously, we can uh, we can we can construct a smaller function like a um, how can I say like a part of this function f that takes only the elements of C and and take them to the set A, and is constructing the same way, taking all of the elements in C. So because this is a disjoint union, the elements in C are just in C, and taking them to the f of C, and that defines a function from C to A. Really, it's the same thing here. So we can state that for every function in this set, the set of functions like that, we can define a unique pair of functions from uh, each one is from different domains, but everyone is for going to the same counter domain. I don't know the name, but is uh, mm, every function will define a unique pair of functions such that at the first, I don't know, the order doesn't matter, but we can think of the first function in this pair will be this f of b as defined here. So notice that the f of b depends of f, and yeah, and the second element in this pair is defined by this f of c that also depends of this function f. So we can think that what we are doing here is that for every function in this set, we are defining a unique function in this whole another set, defining in that way a, a, a how can I say injection? I don't know if that the name in English. So what we're going uh, to 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 prove now is that for every pair of functions we have just one function for every pair of functions in this Cartesian product of sets. We have just one function here too. So we're guaranteeing the other way around. So guaranteeing this way, we're assuring that the sets are isomorphic one to another. So to do that, we can think what properties holds for the set right here. So we can notice that for every function, every pair of functions from C to A, that I denote F2, and from B to A denoted F1, the set of the disjoint union of this set, uh, it's miswritten here. It should be B plus C here, not that A. The set, the disjoint union from of the set B in set C with the pair of functions, the I don't know, that takes the element A, is miswritten here too. Uh, it should be taking an element B from to the disjoint union of B plus C and takes an element B and just drops in this disjoint union. It's really just putting that and another injection. Uh, 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 so we can think that the error is here. The A should be like here and the C should be like here. Thinking this notation. Is making some confusion because it's not, how can I say, it's not matching. The idea is that if we have this this set, this pair of functions that takes from one set to this set A and from another function that takes from another set to this same set A, we can construct first the disjoint union of B and C and the ejections from C to this disjoint union. We'll just pick some element of this set and really drops in the disjoint union. And this disjoint union, we equip it with these injections that is something like that, respects a property, a universal property. So let me see, it's it's miswritten here too. So, but the idea is that the set, the this whole thing that I explained respect this uh, commutative diagram. So with the same idea, we have a set B and a function that goes from B to A like this, and we have a set C and a function that goes from C to A like this, and F2. And we can construct from the set C and B a disjoint union B plus C in the notation, the disjoint union of B and C, and we can construct with that two injections, no? An injection from B to B disjoint union with C that takes an element a little b and goes to an element little b too. It's just putting that the idea of this injection, and the same way with that C, that the injection one I true that goes from C to B right unit with C. And the property that holds with that set with these these injections is that for every pair of functions f1 and f2, there's a unique function from this disjoint union from the set A that we chose at first at random based on this pair of functions here. So that is the universal property that holds for this disjoint union. Actually, the disjoint union equipped with this pair of injections. So we saw that in the earlier slide that for for every function like this from this set to this set, we can construct a unique pair of functions that goes from this set to this, and a unique pair of functions with one of the functions goes from B to A, and one of the functions goes from C to A. And that universal property says to us that for every pair of functions like that, we can construct a unique function from this disjoint union from for that set. So it's just saying what this diagram means. I prefer to think in that diagram, but it's just oops, it's just saying that for different paths uh, are equal to another. So, for example, that expression means the composition of these functions is equal to this function here in the same way from for the other for the other triangle here. So with that universal property and the other result that we saw, we can state that this set of functions are bijective. So the set of functions from the set of functions from this set, the disjoint union to a set A, is bijective to the it's wrong here too. Is bijective to the Cartesian product, not the disjoint union, the Cartesian product of the set of the sets from the functions from B to A and the set of the functions from C to A. And that was really what we needed to prove the that expression. So going back, with we our purpose is to our goal is to prove this expression, and using that those arguments that we saw, we can choose three sets that has cardinalities that match with these three natural numbers that we saw that we see here, and we take these three sets like this, and an equation like that becomes just an isomorphism between these two sets, and an isomorphism between these two sets, thinking that this is the disjoint union. This notation means the set of functions from this disjoint union to A, and this X symbol here is really the Cartesian product between these two sets. So, but this result right here is guaranteed by the universal property that we saw earlier. So we have proven these results that we wanted. But really, uh, I forgot the word, but uh, 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 um, a possible question that we could ask for doing all of this is why. There's no purpose for proving this really simple expression with all of this kind of reasoning. This expression is really elementary, and proving that is kind of easy and kind of really dumb to do that in this this framework of of thinking, and this kind of theory that we are using for this simple expression. And one of the possible answers is that the categorization that we use, the translation actually that we use, helps us to abstract some useless definitions. For example, in the proof that we really use, the sets are not meant to be finite as we stated. So if we chose some infinite sets here, we this statement holds for in the same way. So we can using this reasoning, we can show that for every three cardinal numbers, alpha, beta, and gamma, we this lookalike expression is really the same thing. It's really not the same thing, but it's, it's just the same principle. For those who doesn't remember, the cardinal numbers encapsulate that it's like a generalization of the natural numbers. So they have the finite natural numbers and transfinite natural numbers. So they they really takes place to thinking cardinalities. So that the name is obvious for the reason. So we can extend that result that we proved earlier to cardinals. That and that proof is just the same proof that we just gave. We think of choosing three sets that have this cardinalities, set A that have cardinality alpha and so on. And the structure of the proof, actually the proof itself, is just the same that we just gave. So this process of categorization, this process of translation from one expression to another helps us to see what is really necessary for proving and what is not. So we can even in proving one simple thing, we can extend this proof to proving another thing with the same argument. Another another reason why is that the universal property, in particular the universal property that we saw, serves as a natural environment. Probably it's miswritten here too, but serves for our purpose as a neutral environment for many proofs. So what I mean with that is that uh, if we want to prove a result for disjoint union, we could use this universal property that we saw. But that universal property does not really need to deal with sets. We could use that for topological space. We could use that for groups, for vector space, or even natural numbers itself. So looking for these universal properties is not just it's a waste of time, like thinking the way of there's there's no need to use that in this particular proof, but helps us to visualize some analogies between areas of mathematics that that could be proven by the same argument. So it's, it's like it translating even more for and meta mathematical environment that proves in one way to various areas of mathematics. I think it's kind of poetic this way. So another simple examples of this the same universal properties that we can use to deduce some other results. There's the this notation means the set of the set of continuous functions between the topological disjoint union between two topological spaces to one another is isomorphic in the terms of topological theory. So it's homeomorphic to the Cartesian product from the continuous functions from B from a topological space B to a topological space C, Cartesian product with the continuous functions between C and A. And for this result, what we are using are the same universal property. So thinking analogously with the set theoretical example that we saw and used to prove the elementary arithmetic identity, the set of continuous functions is is like the exponentiation and the set of functions between sets. The disjoint union between sets becomes the topological disjoint union, and the Cartesian product between sets becomes the actually the product topology between these topologies, right? So another way that we can use the same universal property is actually in the natural numbers itself. One could one could argue that that we could how can I say use that framework of thought to deduce that a fraction between natural numbers is like in some quote marks is like a function between two natural numbers, and as is MMC here is like I don't know the name in English. There's sigla in English. It's like the common lower common multiple, and this one is the greater common divisor, I think. So this MMC here of B and C is uh, is like the the disjoint union of sets. So for the case of the natural numbers, and the greater common divisor here, it's like the the Cartesian products of sets or the product topology for topological space. And I know that because this results holds for these other kinds of areas. So the result holds for this universal property holds for sets the same way that holds for topological spaces, the same way that holds for natural numbers, and like this modeling. So just for the proof is the same we use, just using this universal property in in another environment. So just for explanation, what we use in this compact topological space, the addition like is the disjoint union, as I said, the multiplication is the product space, and the exponentiation is the continuous functions from another space to another. And for natural numbers, we use that the addition is like the low common multiple, and multiplication is like the greater common divisor, actually, or multiple, I don't know, probably divide. And exponentiation is like a fraction between numbers. You can think that from if we have a natural number a and we go for with a natural number we go we um, we have a natural number a and a natural number b, and the idea is that this exponentiation is like a function between these two. So a fraction that goes from a to b is just the fraction b over a. So if we multiply this a a times b divided by a is equal to the b that we're going to go. So that's the idea. But another reason that we could use this kind of reasoning, it's nice. It's really cool to use some elementary stuff in mathematics and expand this to another areas. And I think particularly that is really beautiful. It's like revealing some deeper, uh, meaningful stuff in mathematics itself. So, but if you don't know, if you don't agree with me that is nice, it's also appearing everywhere in mathematics. So it's useful for doing mathematics itself. So that was the presentation. The idea here was just to present these ideas from category theory to some elementary stuff that we all know, to to inspire really to use this kind of framework that is translating some result to another place in mathematics, working in that place and bringing back to uh, not only the place we wanted to prove initially, but extending this to another places in all of mathematics. As we saw, we could use in like in topology or even the natural numbers itself in a different way. And that is, I don't know if até foi bom. Mas, okay, so if someone have any questions, I will try to answer. And thanks.
Any questions? Okay, I do. Douglas, do you have an idea? That was really nice, actually.
Mm-hmm.
But
Thanks.
when we think about like real numbers, we can take what you did and do the same thing, because we can also identify real numbers with cardinality of sets, right? But not finite sets now. But can we do that for like complex numbers or something like that,
Can you repeat that for what?
or other number systems, or I don't know?
Yeah, yes. The idea that we use that was valid to us to prove this like result, it, it actually was just using some kind of property that holds for in this case for sets. Like, so if we can model this system of numbers with sets, for example, the proof of this result in this particular system of numbers is just guaranteed in the same way here, because the same structure of proof. But if we could not model this system of numbers with sets, there is even a possible chance that we could trap these results in this system just using another structure. Could be, for example, like even the topology spaces and topological spaces, or even um, some similar systems of numbers that we already proven. Like, actually, for example, this one I made in my notebook, I use for based on the natural numbers itself, based on these results in the natural numbers. So yes, it's really possible not in other systems of numbers, in all possible imaginable systems of numbers. Okay.
Okay, thank you. Any more questions? Okay, so before ending, I believe it's standard to greet the speaker with a round of applause, so everybody can unmute themselves and
Okay,
let.
so can I give you some suggestions of a reference?
Mm-hmm.
Okay,
Well, first of all, the presentation of Douglas was very nice, and thank you very much for the idea and of presenting in English. Thank you very much. So the first reference is a classical. There is the categorification by John Baez and James Dolan that give a lot of motivating examples. And I think that anyone should take a look. The second reference, maybe more advanced, is a talk by Jacob Lurie about categorification of Fourier theory. You can find that in YouTube. Categorification of Fourier theory is the name of the talk. Very nice. That is.
Great, great reference for the case. I
Douglas,
read
you're kind of low,
ah,
your
sorry.
voice.
I read the John Baez uh, recommendation that you said, and the Jacob Lurie video also, and it's really good examples of how powerful this idea of categorization is, and how beautiful in some sense it is to all of mathematics. So yes, great recommendation. Thank you.
Okay, so let's finish this. Everybody, please unmute themselves and thank Douglas for the nice talk. And
Thank you very much. That's very nice.
Thank you. That was very nice too. It seems too powerful